I'm delighted to introduce Abigail Raz, our Math Club Colloquium speaker today. She will be speaking on Union-Closed Set Conjecture. Abigail, the stage is yours.
Thank you so much for having me. I'm very happy to be here in this shared virtual space with all of you. So I'm currently an assistant professor at Cooper Union. Before this, I was a postdoc at the University of Nebraska, and before that, I was a graduate student down at Rutgers. And I work in combinatorics, very broadly speaking, and you'll see a little bit about the things I like to think about in this talk. And I think that what I'll be talking about today emphasizes one of the areas I really like about combinatorics, in that a lot of our questions can be very accessible. We're not going to need a lot to state this really interesting conjecture. And yet it's a conjecture that, despite decades of work, we still don't really have an idea if it's true or not. And maybe by the end of the talk, I'll give some indication on my thoughts on it. But the broad consensus, I think, is that this conjecture could be true. It could be false. We're not really sure. A lot of people have thought about it for a long time, and there's still a lot of work to be done. And so it's a really great kind of place to get your feet wet, to start thinking about these things and have a little bit of fun with some discrete objects. So with that said, let's get started with just some of the basics. I know, so some of you are seniors, juniors, so this will probably be review, but it's best to do it just in case. And throughout the talk, please feel free to unmute yourself and ask questions, put questions in the chat. I'll try to be keeping an eye on it, although I've been mostly teaching in person now, so maybe my chat monitoring skills have declined a bit. So if I don't see something, feel free to unmute, yell at me, I'll see it. Also, if anything on the screen doesn't appear, we'll work on that. Hopefully all the technology will go okay. So the first definition is not really a rigorous definition, but I'll just say that a set is a collection of distinct elements. And you might complain that, well, I haven't defined what a collection is, and so am I really defining anything? But we'll let this go. Everything's going to be very finite and discrete in this talk, so that'll be okay. A subset of another set, B, a subset B of a set A is a set whose elements all come from A, is a set whose elements all come from A. So like with most mathematical objects, we can have a notion of a smaller version of that object sitting inside the larger one, and we normally call that a subobject. All right. What else do we need? We should talk about the empty set. So the empty set is the set with no elements. We'll see this guy pop up a few times. Still want to consider it a set. That's how we'll denote it. Another special set that we'll be seeing a lot, I will denote the set of integers that's just 1 through n by this bracket n. We're going to be seeing this set a lot, and it'll be easier just to have that notation for it. And then last but not least, we should talk about cardinality. So I will say this is the size of A, is the size, which is number of elements in A. All right, and as I mentioned earlier, all of our sets are going to be finite, so we're not going to have to worry about, any kind of difficulties regarding what does size mean when we're talking about infinite sets. Everything is a finite number of elements that we can just count, and the size is exactly what you think it is. So in this talk, most of our sets will be sets of positive integers or families of sets of positive integers, but they don't have to be, right? So maybe I have the set 1, 2, smiley face star, right? That's a perfectly good set. It has size 4. Can someone give me a subset of that set? Just so I know you're actually there behind your little black boxes.
1, 2.
Sure, 1, 2. The set containing 1 and 2 is certainly a subset of the set containing 1, 2, smiley face and star. Excellent. It's worth noting that the empty set is a subset of every set for any set A. Okay, because all of its elements are in A, well, it has no elements, so that is what we would call vacuously true. All right, let's build this up a little bit more. We need one more definition. There will be a few more. The power set, so I shouldn't say the power set of a set A. And this is denoted in a couple of different ways. You'll often see this kind of notation, or what I'll be using is this 2 to the A notation. And we'll talk a little bit why that's a good notation to use and not a terrible notation. This is the set of all subsets of A. Okay, so let's look at maybe a simple power set, and we're going to practice our notation. So this is 2 to the bracket 2. Well, this is all of these subsets of the set 1, 2. So we've got the empty set in there. We've got the set that just contains 1, the set that just contains 2, and the set that contains 1 and 2. All right, so the power set has 4 elements. There's a corresponding picture that goes with this, where we put these subsets in rows according to their sizes, and we draw lines or edges when the sets differ in exactly 1 element. So we draw a line between sets differing in 1 element. Okay, and so we can sort of trace these guys down to figure out subsets, right? 1, 2 has 1 as a subset. It also has 2 as a subset. It also has the empty set as a subset because we can work our way down. Let's draw one more out. So let's go one step up. Here we're going to have our set 1, 2, 3. Well, how many subsets of size 2 are there of the set 1, 2, 3? Anyone help me out? Just the size 2 subsets.
There are 2 subsets of the size 2.
Sorry, so can you give me one of them?
What was the question again? Sorry.
Subsets of size 2 of 1, 2, 3.
Oh, 2, 3, and 1, 2, and 1, 3.
Yep, those all work. So one way of seeing this is, right, we can just delete any one of the 3 elements. Which one am I missing? 1, 2. Okay. Then we have our singleton guys. Let me see if I can draw this in a way that will help. So that one I'm going to want to be 3. And that one I'll have as 1. And then this guy will be 2. And I've written it backwards. And then we have the empty set way down at the bottom. And if we squint a little bit at my picture, what shape is that? Maybe someone not Hannah? She's been pulling all the heavy lifting for you guys. Okay, so be a little bit careful. Say hexagon.
I mean, it sort of looks like a cube, no?
Yeah, so that's what I'm fishing for. So thank you for following the fishing. Right, it looks kind of like a cube. We've got the square there, the square down there. Okay, and then we're filling in the rest of the cube. So this is a cube. All right, a 2-dimensional cube up here, just a square, right? And we could think about higher dimensional hypercubes. Okay, let's go back to why this isn't terrible notation. What is the size of the power set of the set containing the numbers 1 through n? And you can do a notational guess and you'll be right. And then we'll talk about why this is true. So what should this be if this notation isn't horrific? What do you think? Write it in the chat. You can unmute yourself. So what does the notation at least suggest it should be?
2 to the power of n.
2 to the power n, right? If this is not 2 to the power n, we've made a horrible mistake in this notation, right? And why is this true? Well, we can think about how you could build these subsets, right? You go to each of the numbers, 1, 2, 3, all the way up to n, and you ask them, would you like to be in my subset or not? They have 2 choices. They could be in the subset, they could not be in the subset. All of those choices are independent, so there are a total of 2 to the n choices that you can make. Each one of those list of choices exactly defines your subset. All right, so you've got the all no's, that would give you the empty set, the all yeses gives you the full set, and any combination is going to give you proper subset there. Okay, we're going to be thinking about these, so keep this in your head. We need a couple of more definitions before we can get to the fun conjecture, which will be the basis of this talk. This is just talking about unions and intersections of sets. We'll really just need unions, but can't do that without saying intersection as well. So if A and B are sets, then we have A union B. So this is A union B is how we speak this, is the set containing all elements in either set. All elements in either A or B or both. So this is an inclusive or. And then their intersection, A intersect B, again, that's how we speak this, is the set containing all elements in both. All elements which appear in both A and B. So to be in A union B, you just have to appear in one or the other, but to be in A intersect B, you have to be in both of them. So let's just, again, do a quick example, maybe 1, 2, 3, 7. This is going to be A, and B is going to be 2, 5, 7, 10. Can someone give me, maybe I'll give A union B because this guy is the long one. 1, 2, 3, 5, 7, 10. Hopefully I didn't forget anybody. And can someone give me A intersect B?
2.
2 is definitely in there. Is anyone else?
Oh, 7. Yeah.
7 is also in there. Right. So A intersect B is 2 and 7. Right. And we'll notice, of course, that A had 4 elements in it. B had 4 elements in it. A union B had 6 elements in it. A intersect B had 2. Right. This isn't a coincidence here. Right. These guys are being double counted. Okay. Let's see here. Last few definitions until we're finally there. Because we're going to be thinking about sets of sets, I'm going to give them a different name because continuing to say sets of sets just gets a little bit crazy. So I'm going to refer to those as families. So a family, and I'll use script A, is going to be a subset of the power set. Okay, so this is a set of subsets of n. Okay, so the elements of families are themselves sets. Okay, and what's special about the families that we're going to be considering is they're going to be what are called union-closed. So a family is union-closed if for every pair of sets A and B, which are themselves elements of your family, so these are subsets of 1 through n, we also have their union is in your family. Okay, so it's closed under unions. You can take unions to your heart's content and you will never escape this family. Okay. Oh, I also realized I used a bit of new notation here, right? This is, speak this as in or an element of, if you haven't seen this guy before. Okay. Let's go through a couple of examples. So I'll write down 2 families and then you can think for a second and determine for me if they are union closed or not. So I'll let this guy be, well, maybe I'll throw the empty set in there. I'll throw the set 1, 2. I'll throw the set 2, 3, and I'll throw in the set 1, 2, 3. And I'll let B have the set 1, the set containing just 2, and the set containing 1, 2, and 3. All right, and I'll make a little comment before we determine if these guys are union closed or not. I'm going to refer to these sets as members and the individual numbers as elements. So we've got families which contain members, which themselves contain elements, just so we have different terminology for all of these things. So what do we think? We've had a few seconds to think about this. Is script A union closed? Is script B union closed? What do we think? Any votes on either one?
Do you mean that the union of all the members of script A are?
So to be, good question. So to be union closed, it means if you take any two members of the family A, their union is also in that family. So if you take any two members of A, their union has to also be in A. If that's true for any two members, union closed. If it's not true for some pair, not union closed, no go. So what do we think?
I think they're both union closed.
You think they're both union closed? Okay, so let's do it with A. So here we can look at, well, if I take the union of the empty set with any set, it's just going to be that set. So that's certainly fine. These two are both subsets of 1, 2, 3. So if I take 1, 2 union 1, 2, 3, I'm just going to get 1, 2, 3. Same with 2, 3 and 1, 2, 3. And then all that's left to check is 1, 2 union 2, 3. And that gets me 1, 2, 3. So we're good to go. This guy is, yes, it is union closed. I'm still blue. That's okay. All right, what about B? We had a vote from Daniel that this is union closed. How do we feel? How do the others feel? Okay, we got 2 votes to union closed. So why do we think this is union closed?
Because 1 union 2 will be in that 1, 2, 3, and then 1, 2, 3 with any of those other members.
Ooh, okay. So I will be very careful. What you said was true, but what you said is not quite the definition of being union closed. So you said if you take 1 and 2 and you union them, that's in 1, 2, 3, and that's true. 1, 2 is a subset of 1, 2, 3. But that's not quite the definition, right? What we're saying by union closed is that the set A union B, not that it's contained in one of the members of A, but it actually is one of the members. So this guy is not, because the set 1, 2, which is the union of 1 and 2, is missing. That as its own set is not in script B. It's contained in a member of script B, but is not itself in script B. Does that distinction make sense? Yeah, so this is good. This is why I want these examples so that we can go through that, because common confusion. All right. So we need the union to itself be a member of the family. Okay. All right, so hopefully we have a little bit of feeling. Now time is to state our big conjecture. This is called the Union-Closed Sets Conjecture. Okay, and this is from the mid-1970s. There's a fun quote from a mathematician, Peter Winkler, who at some point said something like, this union-closed sets conjecture is well known in every way except for the origin and the answer. So we don't know who first said it. We don't know the original attribution, and we don't know the answer. So some people refer to it as Frankel's conjecture because that is one attribution. But even I think in his original paper where he says this conjecture, he doesn't claim it as his own. So anyways, what is it? This says that any finite union-closed family, except I'm going to have to throw out one really silly family. I don't want to care about the family that just contains the empty set. That's silly, don't like it. Every other one has at least one element. So remember, the elements are these individual numbers here, appearing in at least half the members. Okay, and that is the conjecture. Is it true that for every finite union-closed family, except for the family that just contains the empty set, there's at least one element that appears in at least half the members? Okay, so if we go up to our family that was union-closed here in A, in this case, we actually have that all of the elements appear in at least half the members. So we look at one. One appears in this set. It also appears in this set. Well, that's two. There are 4 members in the family, so it appears in at least half. Same with 2. 2 is actually a little bit of an overachiever. It appears in over half of the members. And then 3 again is barely scraping by. Now, there are certainly examples where not all of the elements, but we don't know if this is always true. All right. We will, let's see, what time are we at? Oh, great. So I'm going to give one of the reasons you might want to care about this conjecture is that there are equivalent formulations, equivalent conjectures, in both the language of lattices and graphs. Both the language of lattices, which is another discrete mathematical object, and graphs. And so this is certainly not a unique attribute of this conjecture, but an interesting one that we have this original language, which I would describe as sort of a set system conjecture. It's in the language of sets and sets of sets. We also have another conjecture that's in the language of lattices, another conjecture which is in the language of graphs. These conjectures are equivalent, which should help us out, because what that means is we have all of the tools from everything we know about set systems, all of the tools from everything we know about lattices, all the tools from everything we know about graphs, and yet we can't prove any of them, right? So even with all of that work, we're still a little bit stuck. And so I will give the graph formulation. If you have not seen any graph theory before, I'll sort of speak through some of the definitions. This is actually pretty recent. So this is only from 2013 that people realize that there is this equivalent graph formulation. And this says it's a formulation on bipartite graphs. So any bipartite graph. And the silly thing you have to exclude here is the ones with no edges. So with at least one edge. Contains in each partite set a vertex lying in at most, so the inequality gets flipped, half of the maximal independent sets. So I know I all of a sudden threw out a lot of language here, which I never define, but maybe we'll just run through a quick example to get a feeling for what this is, and then we'll move on to what's known even just in the set formulation. So I'm going to draw a bipartite graph. I'm going to label the vertices because that'll be helpful to us. Let's see here. I want that edge. I want that edge. What do I want 2 to be adjacent to? Just 4. And let's let 3 be adjacent to both 3 and 4. Okay, so if you haven't seen any graph theory before, right, a bipartite graph means that there are these 2 sets, which I'm drawing on the left and right here, where there are no edges between any vertices within either of those sets. So you look at these three, there are no lines between any of them, and there's no line between those guys. An independent set is a set of vertices. These guys are your vertices, where there are no edges within that set. A maximal independent set means you can't grow that independent set. You can't add another vertex and get another independent set. So can anyone tell me what the maximal independent sets are here? Can someone give me a maximal independent set? So a set of vertices where there's no edges between them, but if you were to add any other vertex, there would be an edge between that vertex and your original set. Break it. I know I might be relying on you guys having seen some graph theory before. Dangerous. Any ideas? What a maximal independent set of this guy is? I'll give you one, and then maybe you'll try to go and find another for me. So one of them is the set 4, 5. Okay, so I'm looking at this vertex that I labeled 4 here, and the one that I labeled 5. I noticed there isn't an edge between them, so it is an independent set. But if I were to add 1 to that set, oh no, 1 is adjacent to both 4 and 5. 2 is just adjacent to 4, but that's still an edge I didn't want, and same with 3. So I can't add any other vertex, so it's got to be maximal. Is there another one? 1, 2. Okay, I agree that that's an independent set. Is it maximal? Could I add another vertex to that and have that set still be independent? Still have no edges within the set? So I'll start writing, but I'm going to claim that that guy isn't maximal. Okay, so can we use the 2 suggestions? So we said 1, 2, that is an independent set. There are no edges between 1 and 2. There are also no edges between 2 and 3. But are they both maximal? Are either of them maximal? Could I add another vertex? Okay, I'm going to get to 2, 5 in a second, but let's finish this guy. Right, I could actually just say 1, 2, and 3. Notice there aren't any edges within these 3 vertices. But again, if I were to add 4 or 5, I'd be in trouble. Okay, and then Andre got the tricky guy here to figure out there's one more maximal independent set in this guy, and this is 2, 5. Right, it's going across here, but there isn't an edge there. And if I were to add any other vertex, there would be an edge, right? There's an edge there. 5 has an edge to 1 and 3, and 2 has an edge to 4. All right, so that is maximal. Okay. And here we can check this conjecture, and we can see that, well, 5 lies in 2 of the maximal independent sets, and there are only 3 of them. So it lies in, oh, sorry, I was trying to go for at most half. I should be going for 4. 4 is only in 1 of the maximal independent sets, which is less than half. And similarly, both 1 and 3 are only in 1 of the maximal independent sets, so at most half. Okay. With that being said, let's start to spend these last 20 minutes or so thinking about what do we know. So we don't know the answer to the conjecture. No, the answer to the conjecture. But we do have some results. So let's look at partial results. Okay, so you guys are all math students. You've been in many math classes over the year. When you're given a statement, which is some universal statement for all, blah, 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 something holds, and you can't prove it, thinking, I just don't know how to attack this. What are some things that you could do to try to get to similar, but maybe easier results? What could you try to do? What could you try to change about the question to start to make some progress, maybe think about how the question is working, and hopefully give you some information on how to prove how to prove the result in general. What might you start doing?
We could try using examples.
Yeah, we could try examples. Absolutely. So I'm going to refer to this as a type 1 type of case because you suggested it first. So I'll say this is like special cases, or another way of saying this is you could like add some hypotheses. So you could say, I only want to look at these very special cases, these particular examples. And this is something people have absolutely done. So we know that the conjecture holds, and these are not all of the results in this world, but it's a flavor of them. So for instance, if n, which is the ground set, so all of your subsets are sets, all of your subsets are subsets of the set 1 through n. It will hold. This is from 2012, Sivkovich and others. In 2012, there had been work in this realm prior to this. In that same paper, they also looked at maybe your ground set could be huge, but the size of your family isn't. So there are only, let's say, 50 things in your family. We can make some good algorithm on our computer and let our computer chug away for a little while, and it can check these things. So those are both in the sort of small subcase side. And there are certainly people, again, I'm not actually sure if this is currently the best, like this might be up to 13 now or something like that. But it takes a lot of energy to push these things up because all of a sudden there's a lot of families, there's a lot of things to check. In the like adding hypotheses world, there are certain special cases. So for instance, if A has a singleton, so one of its member sets just looks like the set containing a single object X. This is actually an older result. This is Svarte and Renaud, and this is from 89. So this is earlier in this kind of conversation, and there are other results of this form. I think, should double check. I think it also holds if there's just a doubleton, and similar to that. And then one other kind of exciting case is when the size of your family is really big. So I'm going to write it in maybe what seems to be a slightly silly way, but I want to emphasize here. If A is a family on the ground set 1 through n, then the largest it could be is of size 2 to the n, right? That's the full power set, and we're only taking certain subsets from the power set. And so this says if your family is at least half the size it could be, then this is true. All right, and this is a result of Karpos in 2017. This is much more recently. It was actually, when I started thinking about this conjecture, this result had just very recently been thought about. There are actually older results that kept trying to improve this guy. So it was, 3/4, and then it was something slightly less and less. And then this was actually a big jump to get it down to 1/2. And it was an exciting result because it used completely different methods. Up to that point, the tools that they were using to lower this guy were basically similar tools, but just refining the arguments. And then all of a sudden, Karpos comes along and says, let's use discrete Fourier methods. And it turns out that using that, you can get this pretty easily. His result is actually slightly better. It's this minus some really tiny constant. But it turns out to get that really tiny constant, it goes from being a pretty simple discrete Fourier argument to a rather complicated discrete Fourier argument, even just to get this tiny little bit. I don't remember quite what C is, but it's very small. So that was exciting, and that's certainly one realm that people have thought about. Another possibility, and I'll call this type 2, is you could just say, well, let's weaken the consequence. So maybe I can't prove that for every Union-Closed family, there's an element in at least half of the member sets. Maybe I could show that there's an element that's in at least 1/10 of the member sets, or maybe 1/100th of the member sets. Sadly, we can't even get that good. So I'll say this is the best, except for I'm lying a little bit. So I'll amend my lie and I'll say best almost, but it's basically the best, and it's the one with the easy proof, is a result from Mill in 94. So we haven't gotten much better. It's the same start of the theorem, and then it's an element appears in at least, well, now we're in trouble. The size of A, well, -1, that's not going to make a difference, over log of the size of A sets. So just remember, what does the actual theorem say? It says in at least half. So the actual, sorry, not theorem, the actual conjecture, wants it to be size of A over 2, right? It wants it to be in at least half the member sets. We can't even get size of A over some really big constant. We're size of A over log size of A. Okay, so this is a little bit sad, but it's the best we've got. And I think because we haven't proven anything so far, and this is after all a math talk, we should get a little bit of proof in here. So I will squeeze this in. Where does this -1 come in the numerator? It comes from a really silly place where we're just going to assume that the empty set is in A, because that only hurts us because, right, there are no elements in the empty set. So it just makes it harder to have elements in a lot of your member sets. And that's where that -1 is going to come in. So let's let A be a family of 2 to the n. So it's all subsets of 1 through n. And we're just going to assume that n is small as possible. So for instance, if maybe the number 3 didn't appear in any of the members of A, we're just going to throw it out and not consider it. All right. We're going to look at a minimal set such that every non-empty member intersects that set. So let S be a minimal set which has a non-empty intersection with every member of A. So I go to every member of A, I take the intersection of that set with this special set S, and it better have a non-empty intersection. There better be something that's in common with both those sets for every member of A, and S is going to be smallest among those. So notice one thing that this minimality implies is that this implies that for all elements of S, there is some A in your family such that S intersect A is just that singleton. So why is that? Well, if it turned out that there was some element in S that was never the sole member of an intersection with any of the member sets of A, that means that that X wouldn't have been necessary. I could throw it out of S and I would still have non-empty intersection with every member of A, in which case my S wasn't minimal because I threw out an element and it still satisfied the condition I wanted to satisfy. Well, this is huge. And this is basically the end of the argument, because since A is union closed, this means if I look at all of the sets A intersect S, oops, A in script A, okay, this is all of the subsets of S. This is the entire power set, right? Because I take well, if I just want the set X comma Y, I take the set which has S intersect A just be X. I take the set which has S intersect B is just Y. I take A union B, which I know is in script A because it's union closed. And then I have S intersect A union B is X comma Y. And I can do this with any set. And so we're in business because this means that the number of members in A has to be at least 2 to the size of S. Well, that's not how I want to write it. What I really want to write it as S is at most log base 2 of A, right? So there is an element in S, much less in all of A, that's in at least, well, I have all of the members of A minus the one that's just the empty set over log base 2 of A, right? Because every member of A intersects S, right? So there's a member of S that's in at least this many, this average. All right. Okay. I'm maybe as the last thing I'll briefly say why I got interested in this conjecture. And so this is maybe the most kind of oddball type of things you could do with this conjecture, which is you could alter the consequence completely. So ultimately, one of the kind of frustrating things about this conjecture is we're just pretty bad at using the union-closed hypothesis. It's a nice thing to say, but it's actually not very usable. And that in all of these other results where we added hypotheses, we're really strongly using those other hypotheses. And we're not just relying on this union-closed hypothesis. So one argument is, well, maybe we just need to practice using the union-closed hypothesis. So let's see if just with that hypothesis, we can prove some other things. And that will give us some idea of what the union-closed hypothesis gives us. And so in this realm, there was a result from David Reimer back in 2003, which I'm not going to actually say what his result was, but it said basically, if A is union closed, something happens. Then it satisfies, and I'll just call it condition R, which if you're curious about what condition R is, I'd be happy to tell you, but it requires a few definitions, and so I'm not going to state it. But this led to the very natural question, which was, is condition R enough to imply that there's an element in at least half the members? Because union closed satisfies condition R, so maybe just condition R is enough. And even though condition R is a little uglier to say, it's actually a lot easier to use. And this stayed a question, and then this was posed to me by my PhD advisor a few years ago, and I realized, no, sadly, condition R is not enough. And in fact, there's a counterexample just with the ground set 1 through 8 that has 11 members, and that's minimal. I did verify that, but it turns out while condition R was sort of appealing, it is actually weaker, and that it certainly is not enough to imply the consequence of the union-closed sets conjecture. So we've got to sort of go back to the drawing board, think more about how we can use that union-closed hypothesis. So there are a lot of other kind of questions, a lot of other tracks people have gone with this. If you're curious about this conjecture, there's a nice survey article that is called, I'm going to get this slightly wrong, but if you Google it, it'll come up, Journey of the Union-Closed. The proposition is probably wrong. Sets conjecture. It's something like that. It's a little out of date. It doesn't have that Karpus result. I think it's from maybe 2014, but it's a nice survey, and it will go through the lattice translation, the graph translation, some of the special cases that are known there. There's also was a polymath project on this. And so if you Google polymath project, you'll see a bunch of people's thoughts on this conjecture. This conjecture that I disproved was on there at one point. There have been people discussing things like, if we wanted to prove this by induction, what would we need to do that? There's actually a recent paper that was posted a few weeks ago that said, this thing that could have been helpful for an induction proof might not actually work. So at least that hope is a little bit dashed. But there's a lot of fun thoughts on that and a lot of variants of the conjecture if you wanted to do some sort of weighting of the elements and think about it that way. If you have a quirky way of changing this conjecture, chances are someone else has been thinking about similar stuff. So it's a fun world to sort of dive into and get your hands a little dirty. But I think I'll stop there. And if you guys have any questions, I'd be happy to try and answer.
Let's thank the speaker. That was fantastic. Abigail, I loved the talk and the way the students were responding, they loved it too. So thank you very much. I'll stop the recording.